Okay, this is going to be my check to see if you did this video. What I want you to do is actually take out a separate sheet of paper. I know, pause the video, complain, do the whole bit, but trust me on this. This is going to help you out. We have a new type, well, it's not a new type of factoring. It's a older type of factoring to learn that we're going to learn in a new different way. Besides, as I'm recording this, there's a power outage in the Super Bowl, so what else are we going to do? Okay, the new type of factoring that we're going to learn, I'm going to give us some space here. We're going to call, you can see from the heading, dots 2. I like to think of this as harder dots, harder difference of two squares. And what the thing is with difference of two squares, and I want you to remember that every single time we factor, number 1, we look at greatest common factor, and number 2, we look at the different kinds of factoring that we can do, whether it's 2-term or it's 3-term. If it's 2-term, we look for difference of two squares. And that's where we are right now. We're going to go back to the 2-term factoring. What I would like you to do is actually do this sort of thing here where we say triangle squared minus box squared equals triangle minus box and triangle plus box. That is essentially the factoring pattern for difference of two squares. So the example I'm going to give you, example 1, I'm going to do x minus 1 squared plus y minus 2 squared equals. And we're going to factor that. This is two terms. This is a term and this is a term. And what this is going to factor into is the first minus the second times the first plus the second. So what I want you to see is that this actually follows, oh sorry, that shouldn't be a plus in the middle. You should be freaking out at me. That should be a minus. This follows the idea of a difference of two squares. So if it's a difference of two squares, what that means is that we're going to factor it into two binomials. And I'm going to make these ginormous binomials. And what I'm going to do is actually draw grouping symbols here, minus this, and this plus this, because difference of two squares factors into two conjugates. So then we look at the first and we say, what's the square root of x minus 1 squared? Well, that's just x minus 1. That's also going to be x minus 1. And then the second one, we would say that that's y minus 2 and y minus 2. Now, as a final step, we're going to clean this up quite a bit. Let me give some more space. So this is actually going to become x minus 1. Let's distribute the negative, minus y plus 2. And the second one was x minus 1 plus y minus 2. This is going to clean up to x minus y plus 1, and then x plus y minus 3. So it's different. It's the same, but it's different. And I hope you can see why it's the same and why it's different. Let's do another example. 64 minus, parentheses, x minus 2y squared. Okay. With this one, this is also a difference of two squares. You see a minus sign in between two perfect squares. The second perfect square is just a little bit of a different way to see it. You see an x minus 2y squared and a 64 is 8 squared. But I'm still going to split this up into two binomials with a minus and a plus. And since the second binomial is a group, I'm going to put it in parentheses. The first binomial is not a group, the first term is not a group, so that just becomes 8 and 8. But this is just x minus 2y and x minus 2y. Notice how the x minus 2y stays identical through this whole thing. I don't actually ever change it. That's going to stay and continue to be an x minus 2y. And that's an important thing to realize in this, because that part can never change. So if I simplify what's inside the grouping symbols now, which you need to do, we have to distribute the negative inside the grouping symbols. I get 8 minus x plus 2y, and then I get 8 plus x minus 2y. Let's do another example. And I'll show you kind of one more way to think about this. We're going to do, let's do x plus 2y squared minus z plus 1 squared. So sometimes what I'll do, and this is just an option, is to say we're going to let a be equal to x plus 2y. And then we're going to let b be equal to z plus 1. And so I'm going to replace that and make it a squared minus b squared. Well, I know how to factor that. That's just a minus b times a plus b. Now I'm going to substitute back. A was x plus 2y. So keeping in mind that we need to keep these in parentheses themselves, I'm actually going to have x plus 2y minus, and my b was z plus 1, big parentheses, and then the second one is x plus 2y plus z plus 1. Now we have to distribute the negatives and just cut out the inside parentheses. X plus 2y minus z minus 1, and then x plus 2y plus z plus 1. And that would be factored. I can't pull that apart anymore. So now that we've done those, let's go and look at this worksheet. This has some examples of some trinomials that are going to be a little bit easier to factor. These are called perfect square trinomials. How do we recognize that? Because if I were to take the square root of that and double it, I would get this. Take the square root of the last term and double it, and you get the middle term. That means that this is going to factor, think about it, it's going to factor into w and w. 25 is 5 and 5, minus minus. It factors into two binomials that are actually the same thing. Which means if we recognize it, we can factor it relatively quickly. And the proper way to express this is actually w minus 5 squared, rather than w minus 5 times w minus 5. And you're going to want to do that. I'm going to make you do that. Write it as something squared, even if it's something times itself. Number 2, I'm going to rewrite it in descending order. If you don't know what the square root of 196 is, but you suspect this is a perfect square, what's half of 28? That's 14, and 14 squared is 196. So this becomes a plus 14 times a plus 14, or a plus 14 squared. Number 3, 225. That would be y. This is a minus here, so minus 225 is 15. If I take 2 times 15, I get 30, so that is y times 15, or y minus 15 squared. Number 4, if this is going to be a perfect square, the first and the last terms have to be perfect squares, and they are. I have a 4q and an r, and if I make the middle term a minus, 2 times r times 4q gives me 8qr, so that is a perfect square. Number 5, if I make this a square root, that's 7b. If I make this is a 3y. This is a minus. Check. If I make that a perfect square, we're going to check that. So 2 times 7 times 3y is not 21, that's 42. Let's double check this. 2 times 7 times 3y. Let's write this by itself and FOIL it back out. I get 49b squared minus 21 minus 21, that's minus 42by plus 9y squared. So these do not match, meaning that this is not a factored form, and since there's no other way to do this, this is probably going to be prime. You could, I'm going to erase this, that you should keep your work there. What you could do is you could separate this out and try other means, but I don't think this one ends up working. Let's cheat and look at the answer key for this. It says prime. So this one is in fact prime, which means that we're kind of done with it. So my point with this was to check the middle term, and that middle term didn't match. So you can't always assume it's going to match. Number 6, a lot of big numbers there. Let's look for a greatest common factor. 81, 18, and 100. No. Now let's check perfect square trinomial because I see a perfect square here and a perfect square there. 9c, 10d, plus, and if I do 9 times 10, I get 90 times 2 is 180. And that is a perfect square. At this point, feel free to work ahead. There's an answer key on the back of, or on the third page, but I'm going to keep doing the rest of these. I'm going to go a little faster. So 25a squared becomes 5a, 49b squared becomes 7b, plus 7 times 5 is 35, times 2 is 70, so that checks. That's a perfect square. This is 11r with a p and a minus. 2 times 11 times is 22, so that is a perfect square. Here I'm going to take out a greatest common factor because it's only 2 terms, and that's the first thing I always check. We've got a k, and we have an m to the third, so we have m squared minus, and then I have h squared. You'd think we'd be done, but look at what's left. We have a difference of 2 squares. So I'm going to keep the km to the third, and I'm going to factor this into m minus h and m plus h. Number 10, if I take out a 20m, I'm left with p to the fourth minus 1, which is also a difference of 2 squares. So I have 20m, p squared minus 1, then p squared plus 1. And this one right here is also a difference of 2 squares. So 20m, p minus 1, p plus 1, and I still have the p squared plus 1 from before. That was not a difference, that was a sum. Number 11. This one's a little odd. If we take out a 1/7, I'd have a 9 minus 36d squared h to the fourth, which, if you look at it, we can also take out a 9. So let's pull out a 9 and make that a 9/7. Then I just have 1 minus 4d to the second h to the fourth. Now, what's left is also a difference of 2 squares, so I still have 9/7, but this is going to be 1 minus 2d h squared, and then 1 plus 2d h squared. So difference of 2 squares in perfect square trinomials, you're always looking for these terms to have perfect squares. Like in number 12, well, let's first pull out a 2, and I have x squared plus 10x plus 21. Okay, that's not a perfect square, but it does look like 7 times 3 is 21 and adds up to 10, so this is going to factor into x plus 7, x plus 3. Number 13. Again, let's pull out a greatest common factor first. I have a 5 and an x to the second. Pull that out, and I have 9 minus 6x plus x squared. Now I'm going to switch that around to descending order. X squared minus 6x plus 9. 9's a perfect square, and x squared is a perfect square. This might be a perfect square trinomial. 9 square rooted is 3. 2 times 3 is 6. This is a perfect square. This is x minus 3 squared. And that's the best way to express that factored. Number 14, pull out a greatest common factor of a 3. I get a c squared plus 9c minus 22. That means that this is 3 times, now this is not a perfect square because 22 is not a perfect square, but 11 times 2 is pretty close to 9. So let's make it 11 and 2 plus 11 minus 2 gets me to 9. Number 15, pull out a 2x squared, and I get x squared plus 2x minus 24. 24, 6, and 4 give me close to 2, so let's think about this as x plus 6 and x minus 4. Number 16, if I pull out a w squared and a z, then I can end up with w squared plus 8w plus 15z squared, 8wz plus 15z squared. Look at 15, look at 8. 5 times 3 is 15, so I have w squared z. Then I have w plus 5z and w plus 3z. And that does get me to 8wz in the middle. So that works. Okay. Next, number 17. If I look at the first and the last, they are perfect squares. W to the fourth is w squared squared, and 1 is 1 squared. So let's try a perfect square trinomial. I have w squared minus 1, because I had that minus, squared. Now this can be a little confusing, because you might be tempted to distribute that square across pluses and minuses, which you know you can't do. But just think, 1 squared is 1, and then 2 times the 1 times the w squared gets you the middle term. So that works. Furthermore, what we have left with it can now be factored. I'm going to put a giant grouping symbol around this, and I'm going to factor the w squared minus 1 into w plus 1 and w minus 1. And that's all squared. And the proper way to express this is actually to express each one of them squared. That is not distributing an exponent across plus or minus. That's raising a power and raising each factor. So that's w plus 1 squared, w minus 1 squared. Number 18, if I factor this, I might be tempted to do this as a perfect square trinomial because that's a perfect square and that's a perfect square, but it's not. That's a minus. So this is going to become a squared and a squared, and then I have 25 and 1. Minus 25 plus 1 gets me to where I need to be. Furthermore, that a squared minus 25 is a perfect square, or sorry, that's a difference of two squares. So that's a minus 5, a plus 5, and then I have a squared plus 1. Number 19, take out a greatest common factor, 5ab squared, and I'm left with, let's see, is that the, oh no, I can't take out the a, so it's just 5b squared, and I'm left with a squared plus, that would be 18a, plus, and that would be 65. 65 is 13 times 5, which adds up to 18. So if I have 5b squared, I can have 8 plus 13, or a plus 13, and a plus 5. Finally, take out a 10, and then a, and I'm left with x squared plus x minus 2. And that would give me an x plus 2 and x minus 1 for my two binomials. So lots of factoring mixed in together. Always greatest common factor first, and then we check the different kinds of factoring patterns that we have.